I'm Jihyeon from the KGSEA Math Circle, and in this lecture, I will explain basic probability theory. So first of all, what is probability? It is the measure of how likely an event is to occur. So let's say we're trying to find the probability of event A. In that case, we're trying to find the total number of outcomes favorable to event A occurring over the total number of possible outcomes. And in that sense, we're trying to find the number of event A over number of U, which is the universal set of all possibilities. There are two types of probability. One is experimental probability and the other is theoretical. Experimental probability is the probability that we're trying to find over experiments. So for example, we're trying to find the probability of the number one appearing, and we're trying to roll it 100 times to find experimental probability. And out of the 100 times that you roll it, one appears 46 times. So the experimental probability of one appearing in this situation would be 46 out of 100. On the other hand, as I said, there is theoretical probability, which is based on theory only. So if we're rolling a dice, the probability of one appearing is just one because there's only one face out of the 6 that shows the number 1. So the probability of rolling a 1 theoretically would be 1 over 6. So in definition, experimental probability is the probability found by performing a series of experiments and observing their outcomes. The formula for this would be probability of experimental experiment is the number of times event A occurred or happened over total number of trials. I'll give an example of tossing a coin. So in this situation, we're tossing a coin 10 times, and a coin has a tail and a head. And these are the only possible outcomes. So it's either heads or tails. So in total, there are 2 outcomes. And since you're tossing it 10 times, let's say heads come out on the top 4 out of 10 times. So the experimental probability of heads will be 4 out of 10. And on the other hand, out of the 10 times, tails comes out 6 times. So the experimental probability of tails would be 6 out of 10. But in theoretical probability is the probability that deals with assumptions in order to avoid unfeasible or expensive repetition of experiments. What this means is that we're trying to be more efficient in terms of finding probability. For example, if you have to conduct an experiment that requires you to spend a lot of money or a lot of time, this would be inefficient. Therefore, you'll find theoretical probability instead. The formula for this would be the number of outcomes favorable to event A out of total number of possible outcomes. So the difference is that in the theoretical probability does not base the value on the number of experiments that you conduct, instead the number of possibilities that you can have. So when tossing a coin, there are 2 possibilities, a head and a tail. And since head is just 1 out of the 2 possibilities, the theoretical probability is 1 over 2. And this goes the same for the probability of heads. Now we'll talk about sample space representation. So sample space is a representation of all possible outcomes of an event. And the set notation would put the elements of a set in curly brackets. So for example, throwing a dice results in 6 outcomes, which are 1, 2, 3, 4, 5, and 6. Thus, to identify the set notation of this sample space would be curly bracket 1, 2, 3, 4, 5, 6. Other than using the set notation, you can show sample space through 3 common ways. One is a table, there's also a tree diagram and a Venn diagram. Starting with a table, this is an example of a sample space representation of throwing die A and die B. So the cross-section shows the sum of what die A and die B would be showing. And the question is, what is the probability that the sum of the numbers showing on the dice is 5 or 10? So you have to look at the cross-section and count the number 5 and 10. So basically, probability 5 or 10 as a sum would be the addition of the number of 5s and the number of 10s in the table, which are in total 7 out of 36 possibilities. So the answer would be 7 over 36. Another way to show the sample space is tree diagram, and this is especially useful when you're finding probability over a series of events. So let's say you're tossing a coin 3 times. So the series of events is tossing the coin 3 times. What is the probability that exactly 2 of the tosses results in heads? In other words, what's the probability of 2 heads and 1 tail? So the tree diagram branches out in 2 ways because there are 2 possibilities, heads or tails, regardless of what you got in the first and second tosses. On the right side, you can see the column of results. And if you count up the number of possibilities where there are 2 heads and 1 tail, you will find 3 in total out of 8. So the answer would be 3/8. Here's a Venn diagram. In a class of 25 students, it is found that 16 of the students like cookies, 5 like both cookies and tea, and 2 do not like either. Find the probability that a student likes tea. So when you're given a situation like this, where you are given the number of students or anything that involves an intersection and those who are excluded from both, you would like to use a Venn diagram. And the first thing that you have to do with the Venn diagram to find the answer is to indicate the intersection and those that are outside of both options. So it's given that 5 like both cookies and tea. So in the middle part where the circles overlap, you would write 5. And outside of those circles in the sample space, you will write 2 because there's excluded and they do not like either cookie or tea. Now you have to find the part where students only like tea or only like cookies. So to find the number of students who like cookies only, you would have to subtract 5 out of 16 because in the total number of 16 that likes cookies, there are those who like both. So you would have to subtract that. That would be 11. So you have the values for the intersection for those who like cookies only and do not like either. Now, the place where you have left is the number of students who likes tea only, and you can find that by subtracting the other values out of the total number of students, which is 25. So that part would be 25 minus 5 minus 11 minus 2, which would equal 7. And here are the representations using Venn diagram for different types of intersections, mainly, for example, A and B, it would be the place of in the overlapping parts in the circles. And you can say that by saying intersection of A and B. The other example is A or B, and that's the union of A or B, and it is the colored part in the second row. The third part is not A, so the complement of A, which means everything except for A, which I'll further explain in the later slides. So the complement is the probability of event A not occurring, and it is written by P A apostrophe. Since the probability of A happening and the probability of A not happening equals 1, like a whole, P not A would equal 1 minus PA. And using the complement is especially useful in finding the probability of at least events. So here's a practice question using the at least event. Find the probability of selecting at least 1 blue marble from a bag of 5 blue and 4 green when 3 marbles are selected without replacement. So this question is basically asking the probability of choosing at least 1 blue marble, which, as I said, would equal 1 minus P not blue. So to find not blue, you would have to multiply 9 times 8 times 7 because you're selecting without replacement, out of 4 times 3 times 2 because you would be choosing only green marbles and they're selected without replacement. The total number of green marbles would decrease by 1 each time you're selecting. And through calculation, you can find the value, which would equal 0.952. Now I'll explain independent and dependent events and their differences. Independent event is when an event does not influence the outcome of the other event. For example, the output of throwing a die in repetition would not influence the next event because each time you're throwing a dice, there would still be 6 faces, and the outcome that you got the previous time does not influence the next row. To represent independent event, PA and B would equal PA times PB. The dependent event is when an event does influence the outcome of the other event. For example, picking cherries from a bag that contain 100 cherries without replacement. Since you're not replacing the cherries that you picked, the total number of cherries would decrease by 1 each time you're picking, and therefore it is dependent on the previous event that occurred. This could be represented by PA and B equaling PA times PB, given that A occurs. And this is conditional probability, in which I'll explain in the later slide. The addition rule of probability states that PA or B equals PA plus PB minus PA and B. So using the Venn diagram, it is easily represented. So from to find the union, you would have to add event A and event B, but subtract the intersection because it overlaps and occurs 2 times in the addition. Here's one practice question. Let's say a bag contains 4 red, 4 green, and 7 blue marbles. They are selected in sequence without replacement. What is the probability of selecting a red, a green, and a blue in any order? Because you're picking in any order, you would have to multiply 6 in the beginning, which is derived from 3 times 2 times 1. And in total, there are 15 marbles. And without replacement, you would have to multiply 15 times 14 times 13, and then 4 times 4 times 7, because you're choosing each color of marble at once. And doing that calculation, you would receive 16 over 65. Practice question 2 is Steven makes 2 shots in basketball. The chance of his first shot getting in is 0.7. If he makes the first shot, the chance of his second shot also getting in is 0.6. However, if his first shot doesn't get in, the chance of his second shot getting in is only 0.4. Find a probability that Steven only makes 1 successful shot. So in this question, you can notice that the probability of his second shots are dependent on how he performs in his first shot. And if you remember, this could be easily represented using a tree diagram. So since the question was asking for the probability that Steven only makes 1 successful shot, you're basically finding probability of his first shot getting in and his second shot not getting in, plus his first shot not getting in and his second shot not getting in. And here you do not have to subtract the intersection because these 2 events are independent and they do not overlap. So by using the tree diagram and multiplying, the answer is 0.4. Now I'll explain conditional probability, which is the probability of event A occurring given that B has already occurred. So you can see the formula, and it's saying PA and B over PB. Here's one practice question using conditional probability. A class of 40 students was asked, do you like math? 5 out of 20 male students said no, and 2 out of 20 female students said no. Find a probability that a student likes math given that they are male. So here, the probability of likes math given that the person chosen is male would equal P likes math and male over P male. So using the table sample space representation, you can find the total number of male students to be 20 and the total number of male students who like math to be 15. So the answer would be 15 over 20, which is 3 over 4. So to summarize this lecture, I talked about what probability is, what the theoretical and experimental probability, sample space representations, complementary events, independent and dependent events, addition rule of probability, as well as conditional probability. To study further on probability theory, you would also like to search about Bayes' theorem. That is it for my presentation, and thank you for listening.